Okay, Assalamualaikum warahmatullahi wabarakatuh. So we meet again for this week, Chapter 2, Introduction to NR Latex. So in this chapter, they are further divided into 4 subchapters, which is the first one is latex structure, latex constitution, biosynthesis of latex, and clone characteristic of rubber tree. So the lesson outcome for this chapter, at the end of the chapter, you should be able to memorize and write the structure of natural rubber latex. This is very important because it might be, you might want to write your own structure and use it for test or final assessment. Okay, and then to state the properties of natural rubber field latex, to list all natural rubber field latex constitution. Okay, there is 4 latex constitution, and to illustrate the biosynthesis of NR field latex. Okay, the first one, the latex structure. Chemical compound can be divided into 2 simple classes. The first one is organic compound which are made of carbon and hydrogen atoms. Whereas for inorganic compound which are not belong to the organic groups, lack of carbon-hydrogen bonds. Okay, I think this is very common for knowledge for polymer chemistry. Okay, later on you will take polymer chemistry, you will or organic chemistry, you will learn how to differentiate the organic and inorganic compound. Okay, latex structure. For example, formic acid is an organic, 2 atoms of hydrogen and oxygen, 1 atom of carbon, and forming a molecule. Whereas for acetone, also an organic, having 3 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen, forming a molecule. Whereas for sulfuric acid and ammonia is inorganic compound because of having sulfur and 4 atoms of oxygen, and ammonia having nitrogen in their structure. So that means for any substance without carbon compound, we call it inorganic compound. Okay, so any organic compound or molecule with carbon structure, we call the organic compound. Okay, latex structure. Atoms in an organic molecule are bonded by sharing their electrons between the atoms. Ionics or most inorganic compounds are formed due to the electrons being donated or being accepted by the bonds atoms. Organic compounds in most cases are non-polar, but they are polarizable. An organic compound. Inorganic compound in most cases are polar. The molecular discussed for above, for example, H2O have low molecular weight and the number of atoms combining to the forms of molecule are not great. Polymer in general have high molecular weight and a lot of atoms combine to form a polymer. Okay, previous chapter, on chapter 1, on introductions, I did mention about the combination of repeating units of monomer to form a polymer. This repeating unit form a high molecular weights of carbon atoms, carbon backbone structure, and produce a high molecular weight. Okay, the polymer are formed from simple organic or inorganic compound repeating to form a polymer. This repeating unit known as monomer. I did mention last chapter the number of monomer in a polymer chain is known as degree of polymerization. For example, repeating units of a monomer A units with degree polymerization with n number of n's. Okay, number of polymerization, degree of polymerization. Okay, polymer normally are made up of a long chain which can be straight chains or branches, long and short, or can be cross-linked. Basic polymer structure having a linear chain which is a stretch. Okay, this is the basic structure of linear chain, and then we have a coil structure at rest. So when you are not stretching your structure of polymer, it will be coil or at rest. Okay, in relaxed state, it will be a coil chain. Latex structure having a short chain branching, long chain branching, or cross-link network. Here you can see a short chain branching. Here is long chain and branching, and then we have tar polymer, also a cross-link polymer, so that it joins to another backbone structure. The black line is a backbone structure. Okay, the cross-link is the blue line, so it ties the backbone structure to form a cross-link polymer. Okay, that one is some sort of the what we call flashback from previous chapter. So this is the main idea of this chapter. Natural rubber is obtained from tree of Hevia brasiliensis, ataupun awak panggil pokok getah lah. Okay, Hevia brasiliensis was found in the Amazon rainforest in 1830. Increasing demand on the discovery of vulcanization procedure in 1839 led to rubber booms in the region. Okay, when they first encountered that Hevia brasiliensis, there is not much can be offered by rubbers. But eventually in 1839, they discovered the vulcanization process to strengthen and to make the rubber is more usable in our daily life, so it became a rubber booms during that time. In 1898, the rubber plantation had been established in Malaya. Okay, this is before our Independent Day. Sebelum kita merdeka lagi lah, 1898. Okay, from Malaya, so they bring the rubber seeds, they plant it in Malaya. Example of latex dip products that being commonly produced is a glove, which is for surgical examination and household. And then we have baby teeth, balloons and condoms. Yeah. And then we go to the latex structure. Previous one, I did mention about the history a bit of Hevia brasiliensis. Now we go to the ideas of the latex itself, which is the latex structure. Natural rubber is a polymer having a long chain-like molecule and high molecular weight. Structurally, the chain is made of isoprene unit as the monomer, and there are about 3,000 to 15 repeating units of this monomer. So, this isoprene unit are repeated itself around 3,000 to 15,000 to form a polymer. The process of joining the monomer will be known as polymerization. So you link each of the monomer of isoprene, we call the polymerization. This is the latex structure, which is the monomer of isoprene with polymerization process we produce a polymer. I did mention earlier about the N in a bracket. N is the degree of polymerization. It depends on the how many of your monomer that link together. And then natural rubber is named as this is IUPAC system name cis-1,4 poly-2-methyl butene. Okay, so later on when you go you take the organic chemistry, you will learn the IUPAC system, the common names of each of the substance, molecule or compound. Okay, although the term cis-1,4 polyisoprene is more commonly used. So in our what we call the polymer technology, the common name for cis-1,4 poly-2-methyl butene, or also known as cis-1,4 polyisoprene. Okay, the rubber hydrocarbon consists of isoprene unit which will combine to form the long natural rubber chain as stated. Okay, this is the structures of isoprene and polyisoprene structure. So isoprene monomer consists of 4 carbon. The first one is first carbon having a CH2, 2 hydrogen with double bond of carbon, and having a branching of CH3 and CH3 with double bond CH with double bond CH2. With this isoprene monomer, they will convert it into 2 types of polymer. Okay, the structure will be trans-1,4 addition or cis-1,4 addition. What is cis and trans? If you look at this structure, the trans having a structure attached to the carbon number, 1, 2, 3 and 4. Okay, both having 1 and 4 carbon structure. However, the arrangement is alternating for trans, whereas for cis, they're having a same side of arrangement. So cis having a same arrangement, trans having a alternating arrangement. And usually for this structure, the commonly produced is cis1 for polyisoprene. Although the trans will be what we call a minor contribution into a polyisoprene structure. And then here the illustration, the simpler illustration I did mention. Okay, so having a cis, the structure will attach on the same side. Okay, whereas for trans having a alternating, so one top, one bottom, whereas for cis from one side, either both top or both bottom. Okay, cis double bond are found in the following position, which is at 1, 2 and 3, 4. Carbon in the isoprene molecule, therefore polymerization can occur in this position to give a change having 1, 4, 1, 2 or 3, 4 link. Okay, during the polymerization, the weak bonding on the backbone structure will be break through and to forms a stronger link for polymerization. Either it will breaking at 1, 2 or 3, 4 carbon to form a 1, 4 or 1, 2 or 3, 4. But in natural rubber, only 1, 4 link are formed in great abundance. So although there is a mixture of 1, 4, 1, 2 and 3, 4, what we call that, reaction during the polymerization. However, the great amounts or the great percentage of natural rubber latex formed at 1, 4 link. Okay, hence so polymerization can consider to be 1, 4 or head to tail polymerization. Okay, so bear in mind, although in polyisoprene latex, there is a mixture of these 1, 4, 1, 2 and 3, 4. However, we consider it is as 1, 4 polyisoprene because of great abundance of the 1, 4 structure. Natural rubber and gutta percha are naturally occurring cis and trans isomer of polyisoprene. These conclusions are based on the following consideration. The specific gravity of the rubber is 0.92 is less than gutta percha, which is slightly denser, 0.96. So, to its melting point, natural rubber crystals at 53 degrees Celsius, gutta crystal at 60 degrees Celsius. Okay. So this is the chemical illustrations of the isoprene converting into a polyisoprene, cis polyisoprene and trans polyisoprene. Okay. Too much to worry about this. Okay. This is usually in class I would like you to draw the natural rubber, cis and trans, which is being known as gutta percha, because during tests or final exams, I did ask students to draw this structure. So I hope you can memorize and practice drawing this structure, or else during the test you cannot draw the actual isoprene, cis 1,4 isoprene. The phenomenon of stress crystallization. Okay, this is very unique properties of rubber or latex. The molecule of natural rubber are made up of long chains of polyisoprene, and the chains are coiled. Okay, at relaxation state, they are coiled. On stretching, so they are coiled during relaxed states at rest. So on stretching, when you stretch the structure, the crystallization can induce and is known as stress crystallization. During the deformation, the chains are able to close contact with each other, forming a crystalline region. So when you stretch a coil structure, they start to realign into a straight line formation, and with the straight line formation, they tend to be close contact to each other. Okay, I think this one the illustration from the amorphous, the realization state. When you stretch, they start to align and they form a semi-crystalline structure. Okay, this is what we call the stress crystallization. So when you stretch the rubber, they will produce a stress crystallization. So the structure can be modified and it can be realigned during a stress. Okay. The crystalline region will produce high tensile strength in rubber. So some of the application require high crystalline region in order to have a good strength in rubber. Whereas when you want to more elastic rubber, you tend to produce more amorphous structure. Okay. The physical behavior of raw rubber may be related to two compounds, which is the viscosity and elasticity acting simultaneously. What is viscosity? Viscosity is the measure of resistance to flow. Okay. The viscosity component are irreversible and account for the cold flow of raw rubber. So high viscosity that means the inability of the material to flow. Okay, ataupun kita panggil viscosity ni ialah kelikatan dia. So lagi tinggi viscosity dia lebih likat. So dia lebih susah untuk mengalir. Okay, in other words of bahasa lah. So you would more understand on what I trying to say over here, the viscosity. Whereas for elasticity, okay, the measure of energy returned by the rubber immediately after a given energy input. The elasticity compound is reversible and account for the bounce of rubber. Okay, I finish the word first. The longer the chain, the greater the average molecular weight and the greater the elasticity. Okay, elasticity ialah elastic. Sifat elastik dia, kekenyalan. Okay, so it measures the energy returns of the rubber immediately after a given energy output. So when you put an energy to that rubber, it will return back or it will bounce back. So this energy is reversible. Okay, so it will turn into another types of energy. Okay, so having higher molecular weight produce a greater in elasticity. That's why when you want to produce high elastic material, you need a high molecular weight of rubber. So that more rubber, more elastic of that your end product that you produce. Next, we go to the ideal condition of cultivation of NR plantation. I did mention earlier about the cultivations of the Hevea brasiliensis in Malaysia. So NR plantation requires some ideal condition in order to produce a good amount of latex to produce a rubber. It is known that tropical region, which is warm and humid weather like Malaysia, Thailand, Indonesia and India, is the most suitable region to cultivate this Hevea brasiliensis. Okay, why? Because having temperature around 27 to 30 degrees Celsius, having annual rainfall not less than 2,000 mm a year. Okay, soil condition which is slightly acidic, which is 4.5 to 6 pH. And then the suitable area need a well-drained slopey area which is no accumulating water. Although we need a lot of water annually in cultivations of NR, but we don't want to what we call that area that can what we call accumulating water that will drown your rubber tree. So usually if you see why in Malaysia we cultivate we planting that rubber tree at slopey area, okay, macam kat bukit-bukit, kat lereng-lereng, okay, it's much more difficult to tapping the tree. However, it is most suitable area for natural rubber plantation. That's the reason why kita tanam dekat kawasan yang berbukit bukau macam tu lah. Okay, so we don't want any accumulating of water. And then natural rubber, actually we go to the Latex constitution. The natural rubber is made up of many non-rubber chemical constituents. Okay, sorry. So it's not only rubber in that latex or natural rubber that you tap. So later on we go through what I did mean about this statement. These constituents may or may not play any parts in the properties of natural rubber. The typical example of non-rubber are amines and phospholipids, which can act as antioxidant. Others may act as accelerator, stabilizer for latex, etc. So, dalam getah tu sendiri, susu getah tu sendiri, dia bukan ada rubber saja. Dia ada non-rubber juga. So, this non-rubber sometimes acting like an antioxidant, what we call the accelerator, stabilizer, etc. And some of it tak ada fungsi pun, tapi they appear in that latex. Okay, next. Latex may be simply defined as a dispersion of polymer material in essentially aqueous medium. Okay, the polymer of rubber particle may be termed the dispersed, discontinuous, or internal phase, and the serum is the dispersion medium, continuous or external phase. So you have a serum, which is the continuous phase, and then you have a rubber particle, which is the discontinuous phase. Okay, here is the illustrations of the serum and the rubber particles. Okay. Next, latex constitutions as follow. The first one is rubber phase. Rubber phase consists of lipids and protein. And then we have bottom fraction or B serum. We have serum or we call the C serum, and finally the free Wesleyan. Okay, so I did mention earlier the first slide, the second slide about the latex constitution having 4 phases. This is the phases that having in the latex constitution. Okay. The latex constitution consists of this percentage of what we call that the composition of phases. Okay, we have dry rubber, approximately 35%, 2% of non-rubber, which is the free Wesleyan, and then 63 of serum combination of bottom B serum and C serum. Okay, the total solid content equivalent to dry rubber plus non-rubber equivalent to 37%. So here in fresh latex for rubber phase, for 35% of rubber phase consists of approximately 33.6% of rubber, 0.5% of protein, lipids, and metal ion. Same goes to the bottom fraction, 15% of bottom fraction and 48% of C serum. And then we have a very small amount, which is 2% of free Wesleyan, that consists of carotenoids and lipids. Okay. Okay. Before I go to the next slide, please memorize this illustration. These amounts of rubber and non-rubber and serum percentage, because it's very important. It's very important. It's very important. So when I repeat, I said it's important. It's more likely to be covered in either test or final assessment. Okay. And then for latex constitution, for rubber phase. Okay, rubber phase itself, in fresh latex, rubber particle constitute of 25 to 45% of the volume of the latex. The rubber particles in fresh latex are protected by complex film containing protein and lipids. The rubber particles are usually spherical with diameter ranging from 0.02 to 3 micron meter, very small. Okay, so the rubber particle size is inconsistent. It can be as small as 0.02, as bigger as 3 micron meter. And the rubber phase are actually protected by a thin layer of lipid, and the outer layer is a protein. Okay, so here the illustrations of 2D illustration. This one is 3D illustration. When you cut through, there is a thin layer of lipid or phospholipid coating the hydrocarbon, and the outer layer will be a protein. Next, the lipids. A group of fatty glyceride. From esterification and glycerol and fatty acid, in here lipids are combined with other ions such as calcium, magnesium, and phosphorus itself. Okay, this is the structure of the lipid, which is triglycerol. Okay, and then we have a protein. Condensation, polymerization, product of amino acid. Proteins molecule contains of pendant amino and carboxyl groups. The pendant amino and carboxyl group account of the amphoteric nature of the protein, since the negative or positive polarity can attain of the influence of the surrounding medium. Okay, I think this one later on I will cover. Okay, I think on stability, latex stability, I will cover on chapter 3, which is the importance of the protein and the amphoteric nature that protect latex from coagulate. Later on, I will discuss further on this. Okay, please bear in mind the stability of latex also contributed by this protein layer. Okay, and then we have serum, B serum and C serum. B serum consists essentially of relatively gelatinous lumps bonded by semi-permeable membranes. For C serum, is essentially aqueous and contains of dissolved material, including metal ion absorbed from the barks of the tree during the flow down the tree. And then the last constitution is free-wrestling. Okay, very small amounts of constitution. A cluster of very hard tiny particles of the yellow-red pigment keratin produced in small quantities as a byproduct of polyisoprene biosynthesis. This is byproduct. They barely contribute any function, but they exist in latex constitution. This is the illustration that we're having a bottom fraction, C serum, free-wrestling, and the rubber itself. Okay, biosynthesis of latex. Biochemically, the polymerization of NR latex plays through many steps, and many enzymes are involved in the polymerization pathway. The biosynthesis of rubber occurs via the photosynthesis and many intermediates. Okay, for the biosynthesis process, including from the carbon dioxide with water, with existence of sunlight, and produce a carbohydrate derived of the acetic acid and enzyme to produce a mevalonic acid enzyme, many steps, and then finally produce the isophenyl phosphate, and then when you tap the rubber tree, they produce the rubber hydrocarbon. Okay, here's the chemical structures or the actual what you call the biosynthesis of latex. Okay, you can go through this one, but nothing much to worry about this, and I don't think you need to memorize all of this, but it's good to know about this. And then the characteristic of different clones of rubber tree. Okay, bear in mind there is a different types of rubber in the world. Okay, even at each of the country, they're planting a different types of rubber clone or rubber tree. Natural latex and caplam is produced from a different clone and tapping condition. Okay, liable to be contaminated with dirt and foreign material, leaf, bark in the tree, thus lead the variability in processing and will give different properties for rubber product application. Care should be taken when handling natural rubber latex and caplams as minimize the contamination. What is caplam? Caplam is here, ataupun kita panggil dalam bahasa Malaysia dia ialah kalau translate ialah getah mangkuk lah, ataupun kita panggil getah scrub. Okay, orang kampung panggil getah scrub. This one is the caplam. If you go to that highway, you lalu dekat area Kedah, sometimes you can smell the what we call the pungent smells of these cup lumps itself. Okay, I think that's all from chapter 2. I hope to see you in chapter 3, and I will elaborate more on the latex stability of the natural latex. By then, Assalamualaikum warahmatullahi wabarakatuh, and thank you.